In this video, we're going to learn to take implicit differentiation. And what that means, it sounds a lot more complicated than it is. It's taking a derivative of a function that's not explicitly defined for y. So it's not explicitly defined for y. An example of that would be y squared plus x squared equals 100. And many of you recognize that this is a circle of radius 10. But as far as implicit versus explicit, this is an implicit equation. And why it's implicit because it's not solved for y. And what we want to do is be able to take derivatives of equations that are not solved for y. So that's what we're doing today. So here's an example, another circle, this time x squared plus y squared equals 25. So we know the radius is 5. And it says write this equation explicitly as a function of y. So what we want to do first, before we learn how to do implicit differentiation, is see how to do this explicitly. So if I were to take this function and solve it for y, I'd get y squared equals 25 minus x squared. So f of x, which is y, would equal plus or minus the square root of 25 minus x squared. Okay, well, then what would be the derivative? What would be my derivative of this function? Well, now that I've defined it explicitly in terms of y equals, I could take the derivative. So the derivative of this equation using the chain rule, and it might help for me to rewrite this as 25 minus x squared to the 1, not negative, to the, just to the 1/2. So the derivative is going to equal plus or minus, using the chain rule, 1/2 times 25 minus x squared to the negative 1/2 times, now the derivative of the inside, negative 2x. And that's what my derivative function equals. And since I have a plus or minus here, I could get rid of that negative sign, so my derivative would equal plus or minus 2x over the square root of 25 minus x squared. And I know this is the first time that we've looked at plus or minus in there, but you could do it with plus, and then you could do it with minus, and recognize that the plus or minus just kind of stays from the function to its derivative. Okay, well, that's what we just did is we took an implicit equation, we turned it into an explicit equation, and then we found the derivative. To do this implicitly, and it's something that sometimes we won't be able to take an implicit function and define it explicitly. Sometimes we won't be able to do that. So when we can't do that, we're going to need a new method. That new method is called implicit differentiation. And so the idea of that is this. What we're going to do is we're going to take the derivative of both sides. So I'm going to take the derivative with respect to x of both sides of the equation. And this is the method for implicit differentiation. You take the derivative of both sides. Now, the right-hand side is easy. The derivative of a constant, well, the constant doesn't change, so its derivative is going to be 0. Looking at the left-hand side, let's distribute that derivative, because we know that we can distribute it across addition and subtraction. So the derivative of x squared plus the derivative of f of x squared. Now, if we continue on with this, the derivative of x squared, well, that's 2 times x times the derivative of x, dx over dx, which we know is just 1, plus, well, the derivative of something squared, of f of x squared, is 2 times f of x times the derivative of f of x. And this here is the big step that we just did. And what we need to be careful is we use the chain rule in both of these cases. When we use the chain rule, uh, you know, when we took the derivative of x, we took the derivative of something squared, which became 2x, and then times the derivative of that something, dx dx. Well, this is just going to be 1. But when we did the chain rule of the other function, this here, the derivative of something squared is 2 times that something times the derivative of the inside, and the derivative of that inside is the derivative of f of x. And that's what we're looking for. So let's see here. Now what we need to do is we need to solve for that. We need to solve for that derivative function. So if we simplify this further, we get 2x, dx dx is just 1, plus 2 f of x times f prime of x, because the derivative with respect to x of f of x is f prime of x, equals 0. Now, solving that, so move this over and then divide, we get f prime of x equals negative 2x over 2 times f of x. Well, at this point, the last step is just to substitute. So then we know f of x. Well, granted, let me stop. We could then leave the problem just like this, and we should. So this equals negative 2x over 2f of x, but I'm going to put 2y. Right, f of x is y. So we get that my derivative function equals, simplifying that, negative x over y. That's my implicit differentiation. If I go back, does this look does that look like what I found up there? Does that, when I found the derivative explicitly, right here, is this the same as this? Why, in fact, it is. Well, first of all, let's correct a mistake I made. That 2 should be gone, because the 2 here and the 1/2, that 2 should be gone. And what I notice is that this bottom, plus or minus the bottom, well, that is f of x. So this is exactly negative x over y, which is what I found here. So in both cases, I found the derivative, one where I found it explicitly and one where I found it implicitly. We need to look at a lot more examples of these for this to become clear. But one thing that you should note is that a lot of times with these implicit functions, I'm going to have y now as part of my derivative. So let's look at another example. So first thing to mention, though, on the Moodle site, there's an implicit grapher on the opening page. There's an implicit grapher, and you may want to use it. I've used it throughout this lecture just as for us to be able to visualize the graph that's going on. So it says here's a graph, and it's implicitly defined because we have y's on both sides of the equation. It says find the slope of the tangent line to the graph of f at of 1 comma negative 1. So we're talking about at this point here. We want to find the slope of that tangent line. Well, to find the slope of that tangent line, we just need to find the derivative at that point. We need to find the derivative at that point. So we need to find dy dx at the point 1 comma negative 1. So to do that, let's take this derivative using implicit differentiation. So we're going to take the derivative of both sides of the equation. And when we take the derivative of the left side, the derivative of y squared, it's power rule, so it's going to be 2 times y, and then times the derivative of y. Well, that's dy dx. And then when we take the derivative of negative 2x, that's just negative 2 times dx dx, but dx dx is just 1. And that equals dy dx. That's the derivative of the right-hand side. So now we're going to need to use a little bit of we're going to need to use a little bit of factoring. So we want to solve for dy dx. So let's move this over, and we get negative 2 dx dx, which is just 1, equals dy dx minus 2y dy dx. Frequently throughout these problems, there's going to be factoring involved. So this equals negative 2. Well, this simplifies to negative 2 equals factor out of dy dx. And what we have left is 1 minus 2y. So dy dx if we divide, is negative 2 over 1 minus 2y. Interesting that it depends only on y. It doesn't depend on x. So we want to find dy dx at this point. So when we want to find dy dx when x equals 1 and y equals negative 1. Well, my equation only depends on y. So to find it at that point, this is going to equal negative 2 over 1 minus 2 times the y value, negative 1, which equals negative 2 over 1 plus 2, which is negative 2/3. And then we ask, well, does that make sense? Looking at our graph, I kind of made a sketch in here. Does that make sense? Down to over about 3. Yes, this makes sense. So there's my answer. That's the slope of the tangent line to the graph of f at 1 comma negative 1. All right, so I'm gonna stop this video, and we're gonna have another video coming up. In the next video, we're just gonna go through more further examples of finding implicit differentiation.